Hello everyone, welcome to the video lecture of this course finite element method. So this is the continuation of the second module, one dimensional problem. So in this module earlier we have discussed the concept of the finite element modeling and what is the discretization, what is nodal displacement, the derivation of the function or the mathematical expression for the nodal displacement, what is the shape function or the interpolation function, how to use those different shape function to solve different numericals. All these things we have discussed earlier considering different numerical examples. So in the last lecture also we have discussed some numerical examples where we have computed the displacement, then strain energy, the stress for different elements, so all these things. So today also, based on those one-dimensional bar elements, we will discuss some more complicated problems and we will discuss the different shape function and stiffness matrix, how to solve those different complicated numericals based on this concept of the shape function and stiffness matrix. We will see and we will try to discuss all those numerical today. Okay, so let us start this lecture. So the first numerical, it states that a thin steel plate of uniform thickness 25 mm is subjected to a point load of 420 Newton at mid depth, which is shown in the diagram. The plate is also subjected to self weight. If Young's modulus is 2 into 10 to the power 5 Newton per millimeter square and unit weight density rho equals to 0.8 into 10 to the power minus 4 Newton per millimeter cube, then we need to calculate the displacement at each nodal point and the stresses in each element. So in this diagram we can see that a thin steel plate of uniform thickness 25 mm is given and a point load, it is acting of magnitude 420 Newton at the mid depth of the steel plate. Different measurements are given for the steel plate, different length, breadth, all these things are given. Then the value of the Young's modulus, then unit weight density, all these values are given. Now we need to find the displacement at each nodal point. So for this case we will have 3 nodal points actually, and stresses also we need to calculate in each element, and in this case we will have 2 different elements. So for these 2 different elements we need to calculate stresses. So we can see in this diagram the numbered within circles, these are actually denoting the elements. So in this diagram you can see we are having 2 different elements and the numbers x without the circles, these are the nodes. That means corresponding to the element 1 we are having 2 nodes, those are 1 and 2, and corresponding to the element 2 we are having 2 different nodes which are 2 and 3. Now for these 3 different nodes we need to calculate the displacement, and for the 2 different elements we need to calculate the stresses due to the application of the force of 420 Newton. So this is the numerical that we need to solve, and these are the data which are given in the problem. Now how to proceed in such numericals. The thickness, it is given here t equals to 25 mm. Now for the element 1, the area you can calculate, which is 100 multiplied by 25, so the area is 2500 millimeter square. Next, for element 2, the area A2, this is equals to 80 into 25, which is 2000 millimeters square. So first we have calculated the areas for these two different elements. Next, we need to the point load is given in this numerical, which is implemented or applied at the mid depth of this bar element. So at point load P, it is acting at the node 2 and it is 420 Newton. The Young's modulus, it is given here, capital E equals to 2 into 10 to the power 5 Newton per millimeter square. The unit weight density rho equals to 0.8 into 10 to the power minus 4 Newton per millimeter cube. So these are the things which are given in the numerical. We have written those first. Now we need to find the displacement at each nodal point. So that means we need to find U1, U2 and U3. Then we need to find the stresses in each element, that means sigma 1 and sigma 2 for the two different elements that we have considered here. Now the steel plate, it is subjected to self weight. So that means we have to find the body force which are acting at nodal points 1, 2 and 3. Now the equation for the body force, that is the column vector F, this is equals to rho AL by 2 multiplied by the column vector 1, 1. So this is the formula for the body force vector F, which is known to us. Now for the element 1, we can write the body force corresponding to its nodes, which are 1 and 2. So that means the forces will be acting on node 1 and node 2. So we have written F1 and F2 in the left hand side, and in the right hand side we need to write rho 1 A1 L1 divided by 2 multiplied by the column matrix 1, 1. The value of rho, it is given here 0.8 into 10 to the power minus 4, and the value of area for this element 1, it is 2500, and the value of its length, it is given to 100. Now if we put all these values, then after the calculation we can find the body force vector F1 F2. This is equals to a column matrix of 20 20. So this is the equation number 1. Next, in this similar manner, we need to find the body force vector for the element 2. And corresponding to the element 2, we are having the two different nodes, which are node 2 and node 3. So that means in the left hand side of this equation, we need to write the column matrix of F2 and F3. These are corresponding to the node 2 and node 3 of the element 2. On the right hand side of this equation, we will write rho 2 A2 L2 divided by 2 multiplied by the column matrix 1, 1. If we put all the values of rho A and L here, then after some steps we will get the value of the force vector as 16, 16, which is a column matrix. So this is our equation number 2, where we have calculated the body force vector for the two different elements. Now if we assemble these force vectors from the equation 1 and 2, then we need to do the matrix multiplication, and we will get the final body force vector matrix, which is a column matrix of F1, F2, F3. This will be a column matrix of 20, 36 and 13. Now, as per the problem, we have seen that a point load of 420 Newton is acting at the mid depth, that is at nodal point 2, which is shown in the diagram. So that means we need to add this 420 Newton in F2 vector, because this 420 Newton is acting at the nodal point 2. So that means the global force vector value finally it will be a column matrix of 20, 4, 56 and 16. So this is the procedure to calculate the global force vector, which is our equation number 3. Now we need to write the finite element equation for one-dimensional plate element. So this finite element equation for the one-dimensional plate element can be represented mathematically. And the formula is F1 F2, this is equals to AE by L multiplied by the element symmetric matrix 1 minus 1 minus 1 1, and which is multiplied by the column matrix of U1 U2. Now for the element 1 corresponding to node 1 and node 2, we can formulate the finite element equation, and which we can write as A1 E by L1, then multiplied by the symmetric matrix and multiplication of the column matrix of the nodal displacements, which are U1 and U2. This is equals to a column matrix of F1 F2, that is the force vector. If we put the values of the area, then the Young's modulus and the length from this element 1 for this element 1, so we can get this equation number 4 after some mathematical steps. We will get this equation number 4. Now in this similar manner we need to form the finite element equation for the element 2. So for the element 2, and which is corresponding to U2 and U3, these two nodal elements or nodal displacement, so we need to write the finite element equation as A2E by L2 multiplied by the symmetric matrix and multiplication of the column matrix, which is U2 and U3. These are the nodal displacement corresponding to the element 2. So this is equals to F2 F3, this column matrix corresponding to the element 2, which are having the nodal points as 2 and 3. If we put the values of the area, Young's modulus and length, then after several steps we will get the equation number 5. Now if we assemble this equation number 4 and 5, that means if we assemble these finite element equations 4 and 5, then we will get one 3 by 3 matrix. So this type of formation of the 3 by 3 matrix from the finite element equation of 2 by 2 for the two different elements we have discussed earlier. So these are familiar to us, this procedure to assembling two different finite element equation. So after some steps we are getting this equation number 6 here. Now we need to apply the boundary conditions. So that is the first boundary condition at node 1. From the diagram we can say that at node 1 there will be no displacement, so that means u1 this will be equals to 0. Again, the value of the global force vector we have already calculated, which you can see here in equation number 3. So this value also from this equation number 3 we can write. So that means we are getting this equation, that means 2 into 10 to the power 5 multiplied by a 3 by 3 matrix, then the column matrix of the nodal displacements where u1 is 0, This is equals to the global force vector matrix, so where the values we have calculated already. Now as the value of u1 is 0, so we can neglect the first row and first column of the k matrix, the stiffness matrix. So that means the reduced equation we can write here. It means 2 into 10 to the power 5 multiplied by 2 by 2 matrix, then multiplied by u2 and u3, this column matrix. This is equals to the column matrix of 456 and 16. From this matrix equation we can do the matrix multiplication, and we will get the equation number 7 and 8 here. From these two different equations we can eliminate the value of the u3 parameter, and finally we will be able to calculate the value of u2, that is the nodal displacement at node 2. So that means we are getting as 1.888 into 10 to the power minus 4 millimeter. So in the first part of the numerical we had to calculate the displacement at three different nodal points. So at u1 this is equals to 0, and at u2 we have calculated 1.888 into 10 to the power minus 4 millimeter. Now we need to calculate the value of the u3. So for that what we need to do, we can put the value of u2 in any of the equation of 7 and 8, and from that we can find the value of u3. So that value of u3 is coming here as 1.968 into 10 to the minus 4 millimeter. So this is the procedure by which following which we have calculated the value of the nodal displacements for the three different nodes in this numerical. Next we need to calculate the value of the stresses for the two different elements. Now the formula for stress, this is equals to sigma equals to E into du dx. So for the element 1 we can write the equation as sigma 1, this is equals to E into u2 minus u1 divided by L1. The value of the Young's modulus and the value of the displacements and the value of the length, these are all known to us, so we can put all these values, and finally we will be able to calculate the value of the stress for the element 1. This is we are getting as 0.188 Newton per millimeter square. Next for element 2, in the similar manner we can calculate the stress for the element 2. So sigma 2, this is equals to E into u3 minus u2 divided by L2. So if we put the value of u3, u2, L2 and the Young's modulus in this equation, then we can easily calculate the value of the stress for this element 2 here, and that value we are getting here is 0.008 Newton per millimeter square. So this is the procedure by which we have calculated the displacement at the three nodal points. That means u1, u2 and u3 we have calculated, and we have found out, and the value of the stresses for the two different elements we have also calculated here. These are the formulas which are actually very important that we need to apply for such type of numericals based on these one-dimensional bar elements. Next, let us discuss this problem which states that we need to consider a bar as per this diagram, and we need to calculate the nodal displacements, element stresses and support reactions. Different measurements are given here, different areas, the lengths, the point load P, these are given here. The value of the Young's modulus and the value of that force or the load is given 400 kilonewton at point P. Let us first write what are the things given in this numerical. As per our general concept, the number with the circle in this diagram that denotes the elements. That means we are having three different elements here. and corresponding to that 3 different elements we are having total 4 different nodes. Now the area A1, it is given 300 millimeter square, which you can see in this diagram. Area is given 300 millimeter square. Then area A2, this is also given 300 millimeter square, and area A3, it is given 600 millimeter square. Then length of the element L1, it is 200 millimeter, L2 is 200 millimeter, L3 it is 400 millimeter. The value of Young's modulus is given 2 into 10 to the power 5 Newton per millimeter square, and the point load which is acting at the node 2, that P is given 400 kilonewton, which is 400 into 10 cube Newton. Now we need to find the nodal displacements, that means U1, U2, U3 and U4. These 4 different nodal displacements we need to calculate. And for the 3 different elements we need to calculate the stresses and the reactions at the support R1 and R2. Also we need to calculate here. Now a similar procedure we need to apply here that we have discussed for the first numerical in this lecture. So first we need to calculate the global force vector. So let us first write the finite element equation, which is given here. The equation which is the column matrix of F1, F2, this is AI by L multiplied by symmetric matrix and multiplication of the column matrix of U1 and U2. Now for this node element 1 corresponding to node 1 and 2, you can write the finite element equation as A1 U1 by L1 multiplied by a symmetric matrix, then multiplied by the column matrix of U1 and U2. This is equals to the column matrix of F1 and F2. Now if we put the values of area, Young's modulus and the length in this numerical, then we will get the equation like this, the last line of this slide. Next, for the element 2, we need to apply the same formula of the finite element equation. So corresponding to this element 2, we are having the nodes 2 and 3. So that means the nodal displacements will be U2 and U3, and the force vectors will be F2 and F3. So corresponding to this element 2, we can form this equation of the finite element equation. So if we put all the values of the area, Young's modulus and length in this equation, then after several steps we are getting this equation number 2 here. Next, for the element 3 also we need to apply the same method. Now in this element 3 we are having the 2 different nodes, which are node 3 and node 4. So corresponding to this node 3 and node 4, we will have the displacements as U3 and U4 and the force vectors as F3 and F4 here. So if we put the values of area, Young's modulus and length in this finite element equation, then after 2 steps we will be getting this equation number 3 here. Now we need to assemble these 3 different equations for the 3 different elements. So that means we will get one stiffness matrix of 4 by 4 matrix. So that means we will get the equation as 110 to the power 5 multiplied by a 4 by 4 matrix, which is the assemblage of the equation number 1, 2 and 3 multiplied by the nodal displacement matrix of U1, U2, U3 and U3 and U4. This is equals to the global force vector of F1, F2, F3 and F4. So this is our equation number 4, which you can see here. Now we need to apply the boundary conditions to find the value of the nodal displacement as well as the value of the force vectors. Now from the diagram itself we can identify this as node 1 and node 4. These are fixed. So if we check this diagram here, you can see that the node 1 and node 4, these are actually fixed. So that means what? This u1 and u4, this is equals to 0. Now at point P, it means at point nodal point 2, 400 into 10 cube Newton, it is acting. So that means F2, this is 400 into 10 cube Newton. And as the self weight is neglected, so that means F1 equals to F3 equals to F4, this is equals to 0. So these are the three different boundary conditions. Now if we put these boundary conditions in the equation number 4, so that means u1 and u4, this is 0, and except f2, all the other forces, these are 0 in the right hand side of this equation. So after this matrix multiplication, we will get this equation number 5 and equation number 6 here. Now from this equations, we will be able to calculate the value of u3, that means the nodal displacement at point or node 3, which we are getting is 0.4444 millimeter. Now if we put this value of u3 in any of the earlier equation of 5, 6, in that case we will be able to calculate the value of u2, that is the nodal displacement at point on node 2, which we are getting as 0.88 millimeter. So that means all the four different displacements we have calculated. u2 and u3 we have calculated here, and u1 and u4, these are actually 0 because the surfaces of the points, these are actually attached. Now we need to calculate the stresses for the three different elements. The formula of the stress, this is equals to sigma equals to E du dx. Now for the element 1, we can write the formula of the stress sigma 1, this is equals to E1, U2 minus E1 divided by L1. So if we put the value of Young's modulus, then U2, U1, all these things are known to us, and L1, this is also given in this numerical. So if we put all these values, then we will get the value of the stress. For the element 1, it is 888.88 Newton per millimeter square, so which is a tensile stress. If the value of the sigma is negative, then it will be considered as a compressive stress. In the similar manner, we can calculate the stress for the element 2. So here we can see that the formula sigma 2, this is equals to E2 into U3 minus U2. So these are the nodes corresponding to the element 2 actually, and divided by L2. So if we put all the values for these different parameters, then we can calculate the value of the stress for the element 2, which we are getting as minus 444.44 Newton per millimeter square, and this is now a compressive stress depending on the sign. In the similar manner, again we can calculate the value of the stress for the element 3, which we are getting as minus 222.22 Newton per millimeter square, which is also a compressive stress. So these are the steps to calculate the stresses for the three different elements. Now we need to calculate the reaction force, and the formula for the reaction force, this is equals to multiplication of the stiffness matrix K and the nodal displacement matrix minus the force vector matrix. And the value of this K, U and F, all these things are known to us. Now if we put the values of all the matrices in the right hand side of this equation of the reaction force, then after several steps and after performing the matrix multiplication, which you can see the different steps are given here. So all these different steps we need to perform based on the matrix concept. Then after some steps we will be getting the value of the reaction forces, that column matrix like this. So that means from this column matrix we can say that the value of R2 and R3, these are 0, and the value of R 1, this is minus 2.66 in 10 to the power 5 Newton, and the value of R4, this is equals to minus 1.33 into 10 to the power 5 Newton. Now, if we want to verify the value of these reaction forces, then we can use that concept. That means reaction force is equivalent and opposite to the applied force. So that means if we add the values of all the reaction forces, so that means R1 plus R2 plus R3 plus R4, this is equals to minus 4 into 10 to the power 5 Newton. So this is the applied force here. So that means this is the final result in this numerical. The nodal displacements, which are U1, U2, U3 and U4, these 4 different things we have found out. In the element stresses, that means for the 3 different elements, the stresses we have identified, and the characteristics of the stresses also we have found here. And finally, the value of the support reactions we have calculated. So these are the procedure and the formula based on which we have calculated the displacements for the considered elements, then the stresses for the considered elements, and the reaction forces, and we have seen how to verify the result for the support reaction. Okay, so this is the end of this lecture. In the next lecture we will try to discuss some more complicated problems based on this concept of the stiffness matrix and shift function. Okay, so this is the end of this lecture.